Here's part D. An experiment 20 milliliters of 0.175 molar HOCl is placed in a flask and titrated with 6.55 milliliters of 0.435 molarity NaOH. Okay, so this is actually happening. So the first thing we want to do is we want to see how much. So I'm going to start off okay, so for letter I, D, single I, the first thing we want to do is calculate the number of moles of NaOH. Okay, so that's pretty easy because capital M, just want this thing to stop there. Capital M equals number of moles per liter, okay, or moles per volume, and the volume must be liters. So that's where we're at. So if I'm solving for moles, that means that I get moles equals capital M times V, or capital M times the number of liters. So we have to change our volume from milliliters to liters for this to work. So that's actually pretty easy. I'm going to plug this stuff in. It is 0.435 capital M, like that, times, and then my, how much is it? 6.55 milliliters then goes to, I go 1, 2, 3 places to the left, 0.00655. Okay, so that's what we're looking at with liters. I just said it. 0.00655. There's a decimal point in there. Okay, and that's the number of liters. Okay, so what you should get from that then, of course, will be 0.00285, and that is the number of moles of NaOH. Okay, that one wasn't too bad. We're just using one equation, our molarity equation, and then we're going to get into, so I'm going to switch to a different color here. I'm going to go back to doing a ice chart, but not for the reason you think. So this is the HOCl. All I'm doing is putting the same stuff over again. Poop. OH minus yields on this side here, H2O, which we don't need to worry about, and OCl minus here. Okay, so here's what's happening. So in my initial concentrations, I need to find what is the number of moles of HOC. So this is 0.00285. Okay, that's the number of moles there. I'm going to minus that because that's the one that's smaller, I'm pretty sure. Let's do this up here. So I'm going to do the same thing. Number of moles equals capital N times V. V must be in liters. So that's going to be 0.175 is our molarity, times, and then 0.020 liters. That's what 20 milliliters is, 0.02 liters. So whatever I get there for that is what's going to go above, where am I at here? There I am. So this is going to be 0.00350 number of moles. And that's for our HOCl. Okay, so over here, all the way down here for my ice chart, and I'm going to need a little more room. There you go. I get 0.00350. So if I subtract the two, okay, like that, what I end up with then at the bottom is 0.00065, and that's the number of moles that are left over. Okay, number of moles that are left over from what? From adding 6.55 and milliliters and 20 milliliters together. This is going to end up as 0. So there's my answer for, so obviously for this over here, there's going to be 0.00285. This one's going to be plus 0.00285, just in case we need this information. We don't need the water, but we may need this, and that is the number of moles of OCl minus. Okay, now the concentration of the HCl here is going to be whatever the concentration is and then I have to add the two volumes together. In other words, the NaOH, I'll write this down here, the NaOH was 6.55 milliliters. The HOCl was 20 milliliters, like that. When I add them together, that'll be, then I'm going to just simply change it to 2655 liters. I add them together and then move the decimal place 1, 2, 3 places to the left, like that. And that turns my milliliters into liters. So now what I have here is the amount of HOCl that is left over after the reaction. That's what the E means, equilibrium, after everything's finished. So you can see that's where I got this number from. That means my concentration then from my HOC would then of course be like that. Now I know this is ridiculous. I understand that there is a lot going on here, but notice that I have that number of moles. Okay, so I'm going to divide this also, 0.2655 liters, and that's going to get me the 0.107 concentration of OCl minus. Okay, so just follow along with everything that I have here. This is a lot of work, and we're not done because the question asks, let's go back up to where the question says, what does the question ask? So the question asks, calculate the OH in the flask after the NaOH has been added. We'll get to that once we calculate this in the flask after the NaOH has been added. So we're going to calculate, so after the NaOH has been added, the OH has been neutralized, but the answer to this question for III, where it says calculate the OH, the answer is not 0 because all of the OH gets used up, that's true, but after we have acid left, then there's some auto-ionization of water that will give us a little bit of OH in the equation. So let's do that. We're going to continue on. This is longer, I'm sure, than you thought it was going to be. I'm going to continue on with blue now as my color. And we're just going to simply start off with HOCl plus water. Yeah, I can't even write water. Like this, making H3O plus OCl minus. Now, we're starting with a 0 here, but not here. You see this up here. This comes down here to be 0.107. This is what they call buffer, when you have something else in the product before we get started. So I'm going to start off initially with 0.0245 as my concentration. Of course, this one doesn't matter. That's not X, that's a dash. That means we're not interested in that at all. Water doesn't change. And I'm going to do another ice chart. I know this is confusing. Please follow along. I promise like this will get a little bit better. Obviously, we have our plus X for the change and plus X for the change there. Now that means for equilibrium, I got 0.107 plus X, and this is just X. And this then, of course, would be 0. That's the worst 0 I've ever made. 0.0245 minus X. And that's where we are. More room. There we go. So that means now that for my Ka, which is still 3.2 times 10 to the negative 8th, I have the same thing that I had before. I'm going to sub in for this stuff, but I get 3 plus OCl minus, like this, and HOCl. This is all exactly the same. So when I plug this in now, what I get is X for this one. I get 0.107 plus X. Guess what I'm going to do with that? 0.0245 minus X. Guess what I'm going to do with that? So let's get this nice and easy. I get rid of this, I get rid of this, because my 5% rule kicks in. Anytime I have a plus x or a minus x, I just get rid of it for these problems. So that makes this actually a lot easier, because now I'm going to have 3.2 times 10 to the negative 8th multiplied by 0.0245, like that. And I'm going to divide then by the one that's on top here, which is 0.107, like that. And then that means x should equal whatever we get for that. Now, what we get for that then is x equals 7.3 times 10 to the negative 9. Okay? That is, in case you're not sure, that is the hydronium ion concentration, like this, equals 7.3 times 10 to the negative 9. Okay. That means then, if I take, remember that Kw is equal to hydronium ion times hydroxide ion, like this. And to solve for the hydroxide ion then, the hydroxide ion equals, and then I would take Kw divided by the hydronium ion, like that. So here I have one answer. That's the concentration of the hydronium ion. And over here, I have 1 times 10 to the negative 14th divided by 7.3 times 10 to the negative 9th equals. This, by the way, is the answer to II. And over here is the answer to III. And this equals 1.4 times 10 to the negative 6th. Like that. See? That was super easy, huh? No problem at all. Don't forget about getting rid of this stuff up here. Do that again. This stuff up here for the 5% rule, and that makes your life so much easier. I know this is confusing. Feel free to rewatch this and see where I get the numbers from.